Hello, and welcome to another DANTE tutorial video, this time on VCarb, our standalone low-pressure carburization process tool. Low-pressure carburization, or LPC for short, is a process where a series of boost and diffuse steps deliver carbon to the material surface where it can diffuse into the part. This process is unpredictable and highly nonlinear, making it difficult to design schedules with trial and error. Unlike gas carburization, where the carbon potential is well controlled by the atmosphere, during LPC the surface quickly reaches the carbon saturation limit of austenite, where carbides are likely to form. Boost steps that are too long or diffuse steps that are too short will not fully dissolve the formed carbides, leading to poor mechanical properties and fatigue for performance. VCarb was designed to alleviate the uncertainties in low-pressure carburization, allowing users to reduce the number of furnace cycles needed to develop new recipes or improve existing recipes. VCarb has two main functionalities, the prediction or the design modules. We will start with the process design to first design a recipe, and then we can modify it in the process prediction module. Starting with the material tab here, we'll choose the selection for the material. We're going to choose 5120 carburizing steel. We'll choose 20 for the base carbon. We could also choose any alloy chemistry or modified grain size that we have for the material. We're going to leave this all default for this example. On the geometry tab, we have radius, load surface area, and model thickness. Slide to show the different options here. So for geometry part type, we choose an inner or outer radius, and that depends on what part of the part you're modeling. Say for this gear here, and we want to model the carburization of the gear flank, we can see that the arc radius is about 6.2 millimeters, and that's an outer radius. If we were modeling more for the core, the root of the tooth here, we would choose an inner radius because it is more of a concave shape, and that dimension here would be 0.762 millimeters. The outer and inner radius has a different effect on carbon uptake, and so modeling the surfaces is very important to capture the case depth and surface carbon. Radii that are 50 millimeters or greater act like a flat surface. Next, we have the load surface area option, and this is used for the carrier gas uptake equation. It really has no effect on the actual carburization analysis, but it is a good at the end of the process to see how much acetylene or whatever your carrier gas is you'll be using based on the carburized surface area of the part. Lastly, the model thickness is used for the analysis to set the maximum depth for when to stop the analysis, and 3 times the case depth is usually pretty good for all of this. So for this analysis, we're going to go with the outer radius and the 6 millimeters like we had shown on the gear on the previous slide. We'll leave the surface area and the model thickness to the default values. Next, we have the process tab where we have 9 options to define the analysis, the desired case, and the surface carbon. The furnace roundup time controls the resolution of the analysis based on the carburization equipment. Some furnaces can control the time to every second, every 5 seconds, or even every 15 seconds. And so this helps make sure the analysis lines up with the actual equipment. The carburizing temperature is self-explanatory, and a temperature of 925 degrees is sufficient for 5120. The gas partial pressure millibar, so this is the partial pressure of the carbon carrying gas or acetylene or whatever you're using. So 1.5 millibar is pretty standard. The effective case depth of 1 millimeter and the carbon at the case depth of 0.35 is sufficient for 5120. Since we're not doing it a full FEA, quenching, tempering, hardening process, the carbon at the case depth needs to be defined, and that would be what is closest to 50 CHRC as a normal case depth. So for 5120, 0.35 carbon should get you close to 50 HRC. The next 3 options here define the analysis. So we define a monitor point just below the surface and a upper bound and a lower bound. And so what happens is when we do the design here, the analysis will boost carbon on the surface until the monitor point reaches 1.1% carbon. And then it'll stop the boost cycle and go turn to a diffuse cycle, or is allowed to diffuse down to your lower bound, which for here will be 0.7 carbon. And then it repeats that process until it reaches your case depth and then the final surface carbon. 0.8 is pretty good for 5120 here for a final first surface carbon when we're looking for about 60 or so HRC. So we will leave 0.8 as well. Lastly, the controls tab has a few quality of life options such as units and efficiency. The temperature has options for degrees C or degrees Fahrenheit, time for seconds or minute, pressure in millibar or torr, length in millimeters or inches, and then the flow rate has several different options for volume per minute. The next two options include the furnace reaction factor, which is used to describe how well the furnace can deliver carbon to the surface of the part. A well-controlled furnace using acetylene with good circulation will use a factor of 1, and any other carbon-carrying gases or any larger volumes or so cycling in your furnace will lower this value. Finally, the carburization efficiency is used to account for the carrier gas lost when changing from a boost to diffuse step. So no process is 100% efficient, so this would allow for that gas, the lost gas, to be accounted for. Finally, the carbon saturation limit can be defined from the DANTE material database, from the current alloy composition defined in the material tab, or user-defined data as far as tabular data. For this work, we'll just use what's in DANTE. With the desired carbon outputs defined, we are ready to run the analysis and view the LPC schedule. So we'll click the Analyze button here, give this a unique name, 5120, 1 millimeter, sounds good. Save this to a good location, temp directory, and it runs the analysis. Within a couple seconds, the Analyze button will plot green, and we know we can plot the design. So this is the final output, the final diffuse steps. If we go to the settings here, we can see all and update the plot. And we can see the boost cycles here have the very high carbon, and then the diffuse cycles diffuse down to this 0.7. At the defined monitor point here, you can see at about 0.2 carbon, we boost up to almost 1.1 carbon, and then at that same place, we diffuse down to 0.7 carbon. This creates a series of boost and diffuse steps that you can see in this tabular data here of about 28 boost and diffuse steps, or about 14 pairs. The total furnace time is about 22,400 seconds, which is just about 6 hours. The boost time is listed here of about 1,000 seconds, and then the total diffuse time of 21,000 seconds is shown here for an R value of about 20.23. So we designed a schedule. We can look at the outputs here at the end as well, so we can choose to uncheck all these and just look at the end. We could also plot alloy precipitates, which would be your carbides that are formed during the process, or the as-quenched martensite hardness, and this is assuming that you get 100% martensite with no other phases at the hardness value that you can get. So for the alloy precipitates in this model, there is 0. It's basically numerical because the 5120 doesn't get up high enough to create these carbides. So for the hardness, we can plot this right now, and we can see that the hardness, if it was 100% martensite, would be about 62 HRC with 100% martensite. We can see that our K-step on the carbon here is we hit 0.35 at that 1 millimeter, and we're just shy of the 0.8 carbon on the surface. From here, before we can change over to the other tabs, we can look at different options that we can change. We can look at what would happen if we carburize this at a little bit of faster speed, let's say 950 degrees C. The higher temperature will increase the carbon diffusion, so we should see a little bit less processing time compared to the other results. If we plot this, we can see now we're a little bit above the 0.8 carbon, and the K-step is a little bit deeper than what was described earlier, but only very, very slight. If we go into the results again, we can see that the boost and diffuse actually has extra steps, but it's down to about 16,000 seconds, or about 4.5 hours as processing time. We can see our processing times are about 50 seconds for the boost on each steps, about 45, 50 seconds. And then the diffuse steps keep growing as the process continues. The last step controls how the carbon is on the surface, the carbon value on the surface. And so you can see that it does not follow that increasing trend here. So if we're happy with this process that we've just designed, we can go to the Boost Diffuse Schedule tab here, and we can see the same thing we saw in the results section. We can see the different step times, the temperature, and the partial pressure of the carbon carrying gas. And we also see the acetylene flow in liters per second. So this boost step would require about 0.0775 liters per second of acetylene to run. We can see this is 30 steps, just like we have prescribed here. And what's great about this is we can export this directly to a text file. Call this 5120 1 millimeter, and it saves it as a text file. You could use that text file in any, import it in any application. And you can also include, you can copy and paste this directly into Excel. So the reason we exported that recipe is we also want to look at the prediction module. So we'll take the prediction module, and all other tabs stay the same after you change the prediction, except for the process tab changes to a tabular data to show the boost and diffuse schedule. Instead of typing all this out, we're going to go ahead and load the text file we just exported. And we can see we have our 30-step process. We can go ahead and analyze that just to make sure that nothing had changed between the import and export. And we will click plot, and we see nothing. That's good. Now we see we do have a little bit of extra carbon here, and from here we can go and modify the process however you need to do to fine-tune it exactly how you need it. So let's say your furnace can only change every 10 seconds. You would change these to, say, 50 seconds each on each one of the boosts, and you can see the outputs from that. So the 5-second ones, 55, we'll have to go to 60 here. This is probably going to add a little bit of extra carbon, and we'll go to 110 here. We can analyze this and see where we're at. And as you can see, we add a little extra carbon here. We are a little high on the case depth, so we can also make changes like remove. We can delete the boost and diffuse, last boost and diffuse step, and see what changes that does to the process. We can see now that since we have such a much longer diffuse, we are down to almost 0.7 here at the surface carbon, and our case depth carbon is a little bit high. So we can change this down to, say, 750 seconds for the last diffuse, which was similar to what was on the last one. And this should bring us much closer to about 0.8 at the surface and about the 0.35 that we were looking for. So we were able to modify the steps to be whole numbers depending on the furnace reaction. Other things you can do, you can modify the partial pressure if needed, and the temperatures through this tabular data, and then see what kind of effect that has. Another thing you can do is say you have this process designed for 5120 and you want to see what that would do to 8620. Something with a little more alloy, but about the same level carbon range, good carburizing steel. So we can analyze this and plot this out, and we can see that we are a little bit lower on the surface carbon here, and on the case depth that has a little slower time diffusing through the part due to the higher alloys here. Another thing you can do is look at a material that has carbide formation. It's like 9310, and we can go into the plot settings here, and we can see the alloy precipitates at the end of the final diffuse process. There are a bunch of carbides here up to about 39 microns in depth. We hope that you enjoyed these tutorial videos and you get some value out of them. If you can, please like and subscribe on YouTube for more content like this. You could always email us at support@dante-solutions.com if you have any questions, or go to our website at dante-solutions.com and look at all the different case studies and video tutorials and stuff that we have on the website. Thank you, and have a good day.